velocity and acceleration in terms of x. So far in kinematics, we've looked at having displacement, velocity, and acceleration in terms of time. But now we want to look at it in terms of x. And we know some expressions already for acceleration. We know that acceleration equals d2x over dt squared, so the second derivative of displacement with respect to time. And we also know it's equal to the first derivative of velocity with respect to time. So we have these two expressions already. And another way we can write dv dt is dv dx multiplied by dx dt. Because here, the dx's would cancel out and we're left with dv dt. But we also know that dx dt is also another way to write velocity. So we get velocity times dv dx. And this is another expression we can use for acceleration. And another way we can write velocity might seem strange, but we can write it as ddv of a half v squared. Because here, this is just finding the derivative of this term with respect to v. And if we did that, the 2 would come to the front. We get 2 divided by 2, which is 1, and minus 1 from the power, and we'd end up with just v for all this term. So this is equivalent to this. And we still need to multiply by our dv dx. And here, the dv's would cancel each other out. And we'd be left with d dx of a half v squared. And this is another expression we can use for our acceleration. So now we know acceleration is equal to the second derivative of displacement with respect to time, the first derivative of velocity with respect to time, v times the first derivative of velocity with respect to the displacement, and the derivative of a half v squared with respect to x. And when do we want to use all of these expressions for acceleration? Now, these two here we'd actually want to use when we have acceleration as a function of time, because we have the respect to time at the bottom. These two we actually want to use when acceleration is a function of velocity, because there's a dv in there, and the v in the second one. And this one here, we want to use when we have acceleration as a function of x. And the best way to do these is with some examples. Let's have a look at one. So we're going to have acceleration equals 3x squared. It's our function for acceleration. And we know initially, so when t is 0, the particle is 1 meter to the right, so x equals 1, and it's moving √2 meters per second to the left, so we know the velocity is minus √2 meters per second, and we want to find the displacement as a function of time. So since we have acceleration as a function of x, we want to use d dx of a half v squared for a, so we're just going to go ahead and sub that in. We have d dx of a half v squared, subbing that in for a. And the reason this is going to work is because now we can integrate both sides, because here we have respect to x and we have everything in terms of x over here. You can imagine, if you like, taking the dx to the other side, and we'll end up with this. And now we can go ahead and integrate both sides. And the integral of d of a half v squared is just going to be a half v squared. And the integral of 3x squared, we're just going to add 1 to the power and divide by the new power to give us x cubed. We get plus a constant. And now we can go ahead and find the value of that constant using our initial conditions. So we know when x is 1, v is minus √2. So we're going to have a half times minus √2 squared equals 1 cubed plus a constant. We're going to get a half times minus root 2 squared is just going to give us 2. 1 cubed is 1. Half times 2 is 1. We get 1 equals 1 plus c, so c has to be 0. So we can rewrite our half v squared equals x cubed without the constant since it's 0. And now we want to go ahead and get v as the subject. So it's times everything by 2, so we're just going to get v squared equals 2x cubed. Then we'll square root both sides, so we get v equals plus or minus root 2x cubed. And now we need to determine, do we need the positive case or the negative case? And we can do that looking at our initial conditions. We know when x equals 1, v is meant to be minus root 2. So if we sub 1 in here, we'll get 1 cubed, which is 1, and 2 times 1, which is 2. And we've got plus or minus root 2, but we know we need minus root 2, so we must need the negative case. So therefore v is going to be minus root 2x cubed. And we're pretty close here because we've changed our acceleration into velocity. We just need displacement now. And we need to rewrite our v as dx dt, and that's going to equal minus root 2x cubed. And again, we have the same problem as before. We can't just, sorry, not as before, we need to go ahead now and integrate both sides, but we can't do that just yet because we have respect to time here, but we don't have anything in terms of time over here. So what we need to do is actually take the reciprocal of both sides. So then we're going to get dt over dx equals minus 1 all over root 2x cubed. And now we can go ahead and integrate both sides because, again, you can imagine taking the dx to the other side and then integrating both sides. So the integral of dt is just going to be t. And we can probably tidy up this right hand side to make the integral a bit easier. We can take out the minus 1 on root 2 and we'll be left with 1 over root x cubed, but we can write that as x to the power of 3 on 2, but with a minus since it's in the denominator, and dx. And now we should be able to integrate this. So we've got t equals minus 1 on root 2. So we're just going to have to add 1 to the power and divide by the power. So we get adding 1 to minus 3 on 2 gives us minus a half all over minus a half plus our constant. We'll tidy this up. So we get t equals, now we've got a negative times a negative is going to give us a positive. So we'll just have 1 on root 2. And dividing by a half is the same thing as timesing by 2. So that 2 can go to the top. And x to the minus a half is the same thing as root x on the bottom. So again, we'll just tidy this up. So t will equal 2 over root 2x plus our constant. And we can use our initial conditions to figure out the value of that constant. We know when t is 0, x is equal to 1. So we get 2 on root 2 times 1 plus a constant. So c must equal minus 2 on root 2. And we'll just rationalize this by timesing by root 2 on root 2. And this is just going to give us minus root 2. We'll sub it back in. So we know t is equal to 2 over root 2x minus root 2. So from here, let's add the root 2 over. So we're going to get 2 over root 2x equals t plus root 2. Let's square both sides. to get rid of the root around the x. So we get 4 over 2x equals t plus root 2 all squared. Then the 4 on 2 will simplify to just 2 over x equals t plus root 2 all squared. We'll take the reciprocal of both sides. So we're going to get x over 2 equals 1 over t plus root 2 squared. And finally we'll times everything by 2. So we get x equals 2 over t plus root 2 all squared for our final displacement in terms of time. Let's have a look at another example. So now we've got velocity equals 3x plus 7. And first thing we're after is an expression for the acceleration. Let's focus on that first. Now, here it would be a common mistake to just go ahead and derive this velocity with respect to time, because we don't have anything in terms of time over here. So remember that acceleration equals d dx of a half v squared, and it also equals v times dv dx. So we've got two ways which we can do this. I'll show you both of them. So the first thing to do is to manipulate this v as a half v squared. So to do that, we'll square both sides. This will give us v squared equals 3x plus 7 all squared, then times everything by a half. We just get a half v squared, and we get a half out the front here. And now we've manipulated this as a half v squared, and acceleration equals deriving this expression with respect to x. So if we take the d dx of both sides, we have d dx of a half v squared, and we'll have d dx of a half outside of 3x plus 7 all squared. d dx of a half v squared, we know that's equal to a. And now we just have to derive the right-hand side with respect to x. So that power would come to the front. We get 2 times a half, 3x plus 7, and we minus 1 from the power to just give us 1. And then we finally times by the derivative of the inside of the bracket, which is 3. And that's going to give us the acceleration equals 3 outside of 3x plus 7. And that's our expression for acceleration. The other method was to use this over here, where acceleration equals v times dv dx. We know v equals 3x plus 7, and from here we can find dv dx. This is just deriving the velocity with respect to x, and that's just going to be 3, deriving this over here. And acceleration equals v times dv dx. So v we know is 3x plus 7, and dv dx we know is equal to 3, so this just gives us 3 outside of 3x plus 7, which was the same as before. Let's look at a second part of the question. So we'll just note down what we had. We know v is equal to 3x plus 7, and now we know that a equals 3 outside of 3x plus 7. And the question is, if the initial displacement is 1 meter to the right of the origin, so initially, when t is 0, the displacement is 1 meter to the right, so that means x equals 1. We want to find the displacement as a function of time. So from here, we know that we have our expression for the velocity. It'd probably be best to start with there since it's closer to the displacement. And we know our velocity is the same thing as dx dt, and it equals 3x plus 7. We want to take the reciprocal of both sides because we want that dx on the bottom. So we get dt on dx equals 3x plus 7. dt dx equals 1 over 3x plus 7. And now we can integrate both sides. So the integral of dt dx is just going to be t. So again, you can imagine the dx on the other side. And now the integral of this looks like it's going to be a log because the derivative of all this is just 3. And we can easily multiply by 3 in the numerator and multiply by a third on the outside. So the integral of the right hand side is just going to be a third times the natural log of the absolute value of 3x plus 7 plus a constant. We can use our initial conditions to figure out that constant. We know when t is equal to 0, x is equal to 1, so we get 0 equals a third times the natural log of the absolute value of 3 times 1 plus 7 plus our constant. So we're going to get c is equal to minus a third times the log of 3 times 1 is 3 plus 7 is 10, and the absolute value of 10 is just 10, and that's our constant, minus a third times natural log of 10. So now we can sub that back in, so we know t is equal to a third times the natural log of the absolute value of 3x plus 7 minus a third times natural log of 10. We can factorize out the third, so we get a third outside of the natural log of the absolute value of 3x plus 7 minus natural log of 10. Let's go ahead and times both sides by 3, so we get 3t, and then we have log of something minus log of something with the same base, so we can bring them all together. So it's going to be the natural log of the absolute value of 3x plus 7 all over 10. Now we're going to take both sides and make them the powers of e. So we're going to have e to the 3t equals e to the natural log of the absolute value of 3x plus 7 all on 10. Then the e and the natural log will cancel out on the right hand side. So we just get e to the 3t equals the absolute value of 3x plus 7 all over 10. Let's go ahead and times both sides by 10. So we're just going to be left with 3x plus 7 all absolute value equals 10 e to the 3t. Now by definition, absolute value gives us a plus or minus result if we have an unknown that's being absolute valued. So we get 3x plus 7 equals plus or minus 10 e to the 3t. Let's go ahead and, well, from here we can actually work out what case we need, plus or minus with the initial conditions. We know when t is equal to 0, x is meant to be 1. So if we go ahead and sub in 0, we'll get e to the 0, which is 1, and we get just plus or minus 10. And when x is 1, we get 10, positive 10, so we know we need the positive case here. So we can rule out the negative case. So we get 3x plus 7 equals 10 e to the 3t. Let's minus 7 from both sides. So we get 10 e to the 3t minus 7, and finally divide both sides by 3. So we get x equals a third outside of 10 e to the 3t minus 7 for our final answer for the displacement as a function of time.